So this is Quantum Circuits 2. The last workshop, we focused on introduction of quantum circuits, and before that, I started off with the fundamentals of quantum mechanics, and we've made a lot of progress in getting towards this deeper understanding of how these circuits work and what each sort of gate does. But now I'm going to take it one step further and introduce a number of new things. So last workshop, we talked about our basis kets. So what are those? Well, those are ket 0 and ket 1. And because, in prior workshops, we've done stuff with the quantum mechanics and the energy levels, we're able to sort of tell that these basis kets correspond to energy eigenstates. And those eigenstates come from the Schrodinger wave equation. So you see there's a lot of intricate sort of physics interplay going on here, but it's very useful for understanding what's going on. We built off that understanding by introducing these qubit gates, or single qubit gates. So they only target a single qubit. And I covered a lot of them in that last workshop. So the Pauli X, Y, and Z gates, these have a natural quantum mechanical basis in the fact that these originate from the Pauli matrices. And the Pauli matrices, I didn't really give too much of a mathematical definition here, but they are commonly used when describing certain spins of particles. And they just have a very elegant one-to-one relationship when it comes to being applied to qubits. I mentioned the handy-dandy Hadamard Gate, which puts us in a perfect superposition. So what do I mean by that? Well, there's a 50% chance you'll be in ket 0, and there's a 50% chance you'll be in ket 1. But I noted that when I introduced the Hadamard, I showed you guys that block sphere, and you note it's a sphere. So it's not just a circle that you're either like, 50% chance of one or 50% chance of this. Doesn't really encapsulate the amount of information or processing power we have at our disposal, because we have gates like S, otherwise known as the square root of Z gate, because this is a pi/2 rotation. So not only can we change the sort of longitudinal orientation of our vector, but we can also change the rotation of it along the sphere, or the phase. That's the more official term. And T and T dagger are intimately related to S. These are just pi/4 rotations. So if 2 pi is a whole rotation along the sphere, then just a pi rotation, or pi/2 would be a quarter, and then pi/4 would be a half of a quarter. So it'd literally be an eighth of rotation there. And then we have a more generalized phase gates. So Rx, Ry, and Rz, rotations along the X, Y, and Z axes of the sphere, and the phi gate, which is an even more generalized R gate. So if I have phi, it takes 3 parameters, and I can essentially describe any arbitrary position along the block sphere, which is particularly powerful. And these kind of funky looking gates here have a strong correlation or relationship to what I introduced as a bit of an appetizer, which is the idea of these universal gates. So universal gates are essentially come from the fact that, like in traditional computing, you use a lot of logic gates, and, or, XOR, NAND, NOR, all of these traditional logic gates. And basically, you can boil down that wide variety of gates into maybe 1 or 2 basis gates. So with those 1 or 2 gates, you can build literally any other gate you want. So with universal gates, these are collections of quantum gates that are universal enough that you can build any other configuration you want. And I will be showing a really cool example of that near the beginning of this workshop. And the reason this is such a powerful idea is the fact that there are an infinite number of unitary matrices, or the matrices that satisfy the constraints to be quantum gates. But they aren't always realizable or implementable in physical hardware, which, physical hardware is always a very finicky thing. We're dealing with error, noise mitigation, so on and so forth. So we basically have the ability to boil down any gate we can think of into a set of these universal gates. And more often than not, we will see that universal gates are easier to implement in hardware, these basis gates, than trying to find some one-to-one hardware mapping between, say, any unitary matrix and something in hardware. So that's why I introduced those universal gates. But you'll see in today's workshop a much more hands-on example, besides me just kind of doing this hand-wavy stuff that I'm doing right now. So here's some objectives that I had for today. But Amir is a very he comes to a lot of the workshops, and he pointed out an error or problem that I had with my prior workshop, which is that my explanation for what it means for a matrix to be Hermitian, a Hermitian transpose, was a little sloppy. So I've opted to spend some time today to kind of clarify that and really solidify our understanding of what that means. And furthermore, we're going to dive into 2 and 3 qubit gates plus quantum states. So what do I mean by 2 and 3 qubit gates? Well, those are essentially the same matrices we saw before, but they've been scaled up so they can work together with 2, 3, and more qubits than the original 1 qubit gates. And I also have to go over quantum states because we represent the quantum states as a kind of ket. So it's just a vertical vector that encapsulates the coefficients of probability. But as we add more and more quantum states, there's a very special operation we have to conduct mathematically to allow us to kind of conjoin these independent states. So I'm going to go over how do we represent them and how do the gates that target multiple qubits, what exactly do they do? And furthermore, I'm going to really investigate what I meant by universal gates, because I just brought up, the Solovay-Kitaev theorem. We can generate arbitrary approximations along the block sphere if we just keep adding more and more gates and in polynomial resource complexity. But that's stuff from the last workshop, and I won't go too far into that definition. I'll just give a preface of it so I don't bog the whole workshop down with just one part of it. Although it is quite interesting. So we're going to go onwards to the Jupyter notebook that has all the examples that I have. And once again, if there are any points of concern, corrections, or questions, please do feel free to unmute yourself, and I will be more than happy to answer your questions. Yes, so special thanks to Amir for clarifying this. We'll start off with clarifying matrices. So I keep mentioning this idea of a matrix being unitary, and I've sort of embedded this idea in your heads that for a matrix to be unitary, it satisfies the fact that if I apply it on a vector, it maintains the proper magnitude. So you remember the block sphere, the vectors we're interested in always touch the surface of the sphere. And that's a property of a unitary matrix. If I shove a vector through the matrix, I perform multiplication essentially, and I get another vector out, that other vector is guaranteed to be somewhere on the sphere, which is just a property that's enforced as part of the probability amplitudes that we were looking at last time. And the probability amplitudes being, if I said 50% of 0 versus 50% of 1, the chances, if I take the absolute value of those coefficients, square them, add them together, they all have to equal 1. And we can visually confirm that quantum property just by making sure this vector is touching. It has to touch the surface of the sphere. If we have a vector that goes outside of the sphere or is not touching the surface of the sphere, we consider that an impure state or even a thermal state. And when you start studying noise in quantum computing and thermal errors, that becomes relevant. But for now, we live in la la land. Everything is absolutely perfect, so we don't have to concern ourselves with that. So that's what it means for a matrix to be unitary. But these unitary matrices have a number of distinguishing properties. And one of them is if I take the matrix times its Hermitian, the Hermitian transpose or the Hermitian conjugate, and I remind you that the Hermitian conjugate is if I were to take let's go ahead and, so this is, this is some random matrix for now. Don't worry too much about what it is. The Hermitian transpose, essentially, if I take the conjugate, so you notice how there are some imaginary values here, like this is a real, and the imaginary values have a real part and this imaginary component. So if I take the conjugate, I'm essentially flipping the sign in front of the imaginary part, and then I were to do the transpose of that matrix, so each row you see here becomes a column, then that becomes essentially the Hermitian transpose or Hermitian conjugate. Yeah, there we go. So the conjugate and then the transpose. Or I just do S dot H, which is the same thing. It just takes the Hermitian transpose or conjugate of the matrix. So all quantum gates need to satisfy the property that taking the Hermitian conjugate and multiplying it by itself gives the identity matrix. So that's what we mean by unitarity. So if I have U times U dagger, and the dagger is something it comes up very frequently in quantum mechanics. It just means I've taken the Hermitian conjugate of the matrix. So U times U dagger is equal to U dagger times U, which is equal to the identity. But if you, the real thing to focus on here is that taking that Hermitian conjugate will give us the inverse of our matrix. And you know, from basic linear algebra, multiplying a matrix by its inverse is guaranteed to give you the identity matrix. So let's kind of, so this S matrix, I kind of lied in the beginning. It isn't any random matrix. It actually is a quantum gate. And so let's kind of remind ourselves what the S gate does in the first place. So here's what ket plus is a state that you can get from applying a Hadamard to a qubit that is in the 0 position, that is in ket 0. So if I did the following, so if I did H times 0, then we get this plus state. And when we're in plus, our vector is kind of pointing outwards like that. Now what's going to happen here is if I apply the S gate, so applying a gate literally means perform matrix multiplication against the vector. So I've just done the multiplication here. And you'll notice that we've done this rotation essentially, a pi over 2 rotation from here to here. So just, you know, to recap, we started here, I apply the S gate, and we rotate, so we change phase, and now we're pointing perfectly in the positive Y direction. That's what S does. But let's see if S really is a unitary gate. So if S is unitary, then it has to be the fact that S times S dagger gives us the identity. Furthermore, if I invert the order, I still get the identity, and that's an important property. This order thing is very important in linear, it's a property of linear algebra and matrix multiplication. Not only do the dimensions of your matrices and vectors have to match, but the order that you put things in will also have a huge impact. And furthermore, we want to make sure that the dagger is really the inverse. So, you know, once again, dagger is the Hermitian conjugate. So if I take the Hermitian conjugate of S, it should be equivalent to the inverse of S. So here I've done a little bit of sleight of hand here. These are just some nice tools that NumPy gives us. Array equal, despite its rather confusing name, can also perform matrix equality. So it can check that 2 matrices are identical. So what I've done here is I've said, okay, so if I do S times its S dagger, or the Hermitian conjugate, I'm going to compare that to the identity. So I2 gives me an identity matrix, or a 2 by 2 identity matrix. So this is a 2 by 2 matrix, 2 by 2 identity. The dimensions are fine. And we'll notice that we get true. Okay, great. So I've just confirmed one of the properties of it being unitary. But let's make sure that the ordering doesn't change anything. So I've gone ahead and, you know, changed the order of the multiplication, and we still get true. Okay, looks good, but we've got to let's do one last check. S dot H should, or the Hermitian conjugate of S should be equal to its inverse. So you see, I do this thing here, NP dot, you know, linear algebra dot inv. So I get the inverse of this S matrix, and we check if they're equal, and they are. Okay, that's great. So we have just confirmed that this matrix is in fact unitary. And to reiterate, if a matrix is unitary, that means that if I take its Hermitian conjugate and I multiply it by itself, regardless of the order of that multiplication, I am guaranteed to get the identity matrix out of it. That's what we mean by unitarity. Now, there's another note that I have to make here, is that S is not self-reversible, but it is still reversible. So what do I mean by that is if I keep applying S, we'll get back to the same place we started. So let's go back here. This was no rotation applied. I just started here. If I apply S, I get here. If I apply S again, I don't go back here. I just keep rotating. Granted, if I apply S multiple times, or I apply another bunch of phase-changing gates, I could return to my original position. So what unitarity guarantees is that for any given action on the vector, I can revert the action or go back to where I started. But it does not have to guarantee that the matrix is self-invertible or the matrix is its own inverse. Some quantum gates do have that property, that they are their own inverse, but the large majority of them do not. So I'll give an example of what I mean here. So some gates are self-reversible, and this is where I have to make the distinction between when we call a matrix Hermitian versus a non-Hermitian matrix. So Hermitian and non-Hermitian matrices. Hermitian and non-Hermitian. Now, we cannot confuse that with the Hermitian conjugate. The Hermitian conjugate is an operator. It is something you do to a matrix. Whereas being Hermitian or being non-Hermitian is a property, a fundamental property of the matrix. I can't manipulate the matrix to make it turn into a Hermitian one, but it's just something the matrix already has essentially. So when a matrix is Hermitian, that means that if I take, that means that by itself, it's already, its inverse. So if I did U times its inverse, U times it should equal the identity. So, but not all quantum gates have to be Hermitian. It only, they have to be unitary, but they don't have to all be Hermitian. The X gate is a fantastic example of what we would consider both a unitary and Hermitian gate or Hermitian matrix, in the fact that if I apply X times itself and X is its own inverse, I should get the identity. So if X is its own inverse, multiplying it by itself should render the identity matrix. And lo and behold, that is true. And we can also visually confirm any Hermitian operator from the fact that if I apply the gate twice, I'll end up back where I started. So here's ket 1. So we're now in the 1 state. Our vector is pointing down. And if I apply X, okay, now I'm in ket 0. I've inverted my state. But if I apply X yet again, I've literally undone what I just did. That is what we, so that's a unitary and Hermitian gate. But that's not the truth for all of them. So let's see what happens to a non-Hermitian matrix. So off the top of my head, the T gate should be a terrible candidate for this, which is great because for demonstration purposes, I need something that makes a terrible candidate. So it doesn't reverse what it just did upon a second multiplication, and it probably doesn't satisfy the property that T times T equals I. So remember, for Hermitian matrices, it is its own inverse. So this, if it was Hermitian, oops, that's weird. There we go. If it is its own inverse, multiplying it by itself will just render the identity matrix. So if I do the test again, so T times T, and then I compare that to the identity matrix, lo and behold, it's false. So that just means that this gate is still unitary, but it is not Hermitian. It is non-Hermitian. So all gates are unitary, but not all unitary gates are Hermitian. So we have to, within the class of unitary gates, we make the distinction between Hermitian and non-Hermitian. So that's why I wanted to put this example out and kind of really clarify that explanation, because as we get into more advanced gates, or as you start playing with your own quantum circuits, having that knowledge is incredibly useful. So once again, thank you so much to Amir. I'm a little saddened he's not here with us today, but nonetheless, I'm still very happy to have had that pointed out to me. And furthermore, to have the opportunity to make sure you guys have a very strong and proper understanding of what it is. So let's go on into these the multi-qubit states. Because up until this point, we've sort of been in this kind of imaginary world where all the gates are restricted to 1 qubit. And we mentioned that the states are just represented by a singular vector. And that vector might look something like, here we go. Let's actually kind of show it to ourselves. Ket 1 is just this vector with 0 is our first element and 1 is the second element. And if I did ket 0, it's just the other way around. 1 is the first element, 0 is the second. And you might get kind of misled by the fact that it says matrix here. But the reason is these lessons kind of use my own implementation of a very primitive kind of quantum simulations library. And I opted to use the NumPy matrix class because the matrices have a lot more built-in functionality than the standard vector class does for NumPy. So that's why you see this matrix thing here. Just treat it as a vector. Like internally in your minds, it is a vector, and that's it. There's nothing too different about it. So in order to express the state of multiple qubits, we have to take the Kronecker product. The Kronecker product is very similar to matrix multiplication, except at the end of your multiplication, you don't perform the element-wise addition. So you don't like scrunch everything together through addition. You just kind of leave it out as it is. So you'll notice that if I do the Kronecker product of 0 and 0, this should give me ket 0, 0, and this is what it looks like. And if I do the Kronecker product of 0, 1, I should get ket 0, 1, and it becomes this thing. So notice how these two kets give us a sort of 4-element vector. And the way I want you to think about this is when we have a 2-qubit state, this is what the probability distribution essentially looks like. So you have, a coefficient for what chance you could measure 0, 0, what chance you measure 0, 1, what chance you measure 1, 0, and what chance you measure 1, 1. So we have 4 possible coefficients. So you remember for our original single qubit state, you only had 2 coefficients, which either dictated that you could be in state, one of the states or the other state. Whereas now we have 4 possible states for 4 possible coefficients. And we still have to classify, or we have to satisfy the condition that taking the absolute value of each coefficient and squaring each of them, and then you add it all together, should equal 1. And why do we need this property? This is known as normalization in quantum mechanics, and it just makes it so that the probabilities all add up to 1. I mean, it doesn't really bode well for us, or it doesn't really play nice with us when we bump into situations where, you could like one day bump into me and ask, oh, what's the chance of it raining? And I told you, oh, it's 120% chance. And you're like, how did you, it's a very inconvenient probability to work with, which is why we normalize things. But this also makes sure that this is a coherent quantum state. So if I were to plot these 2 qubits on 2 Bloch spheres, the vectors are still touching the surfaces of the spheres. They aren't weirdly retracted in, and we aren't overshooting the surface. So we know we're not dealing with some weird thermal state or impure quantum state. And the way I read these vectors, this is my way of reading these things, and I want to introduce this trick to you guys, is we can also use the coefficient per row method to keep track of things. And what do I mean by coefficient per row? Well, if we look at this, it's just, it's got 4 rows here, 4 entries, 4 rows. And each of these rows actually corresponds to one of these coefficients. So if we look at the first row, the value in the first row corresponds to the coefficient of 0, 0, second row, 0, 1, third, 1, 0, and the fourth is corresponds to 1, 1. So there's a 1 it's in the 4th row, and I know that corresponds to this binary 1, 1. So I can tell that we are in the 1, 1 state. And the way you can memorize the ordering of these, like, 0, 0, 0, 1, 1, 0, 1, 1, is just increment by 1 in binary as you go down. So, this is in decimal, this would be 0, this would be 1, 2, and then this would be 3. So that's just, you're just counting in binary, but you're just going downwards. I also have built-ins, so the NP quantum library is what I call it. And if you're really curious, this is like the actual, this is the actual library that I've written with a number of handy mathematical shortcuts that I like using. But there's a built-in ket 0, 0, and if we look at this, I think you guys at this point can sort of tell. Okay, so this is 0, 0, this is 0, 1, this is 1, 0, this is 1, 1. So we know there's a 1 in 0, 0, so I can definitely tell that there's a 100% chance we are in the ket 0, 0 combination. So, and Qiskit also allows us to visualize multiple qubits. So each qubit kind of gets its own Bloch sphere. Now, with that being said, I have to give you guys a bit of a disclaimer when it comes to using Qiskit. For the most part, our intuition kind of leads us to believe that when we read these states, like, ket 0, 0, ket 0, 1, ket 1, 0, ket 1, 1, the most significant bit is on the left and the least significant bit is on the right. So what do I mean by most significant and least significant bit? Well, if I give you a number like 1, 1, 1, 1, 1, 1, 1, which is in binary, if the least significant bit is on the right, then this bit just sort of contributes the least, like it's equal to 2 to the power of 0. Or this single bit that I've kind of spaced out here. But if it was the most significant bit, then it would be 2 to the power of, let's see, 0, 1, 2, or 0, let's see, 1, yeah, 2, 4, 8, 16, 32. So this might be 2 to the power of 32. So that would mean that the ordering is flipped. Naturally, when we read numbers in decimal, if I give you the number 1024, you know that this 4 in the ones place means like it contributes the least. So it's the most significant, the least significant digit. Whereas, this 1 in the thousands place contributes the most. So it would be the most significant digit. So if we look at this, and I've created, this creates ket 0, 1, so the Kronecker product of ket 0 and ket 1, this creates 0, 1. But if you look at this, why did Qiskit give us 1, 0, 1, 0? We told it 0, 1, but it gave us 1, 0. So what's going on here? What is this tomfoolery that IBM wants us to believe in? Well, it has to do with the fact that this is actually a common thing that Qiskit and QASM, QASM is the quantum assembly language, where they choose the most significant bit to be on the right rather than the left. So if you look at this, ket 0, 1, so actually you're supposed to read this 1, 0. So then you know, this becomes 1, 0. But I've been teaching you guys to read it, you know, left to right, so 0, 1. And I'm telling you, for the large majority of examples, excuse me, you will not have to worry about this this weirdness, you know, with the ordering. Like, just read it like you would normally would in decimal. I guarantee you, for all of my examples, I always enforce just like the way you would normally read numbers in decimal. But for Qiskit, I want to give you the warning that Qiskit assumes the reverse ordering, and it just, you know, it can lead to some confusion. Now, with that out of the way, now that you know how to construct these sort of 2-qubit states and how to visualize and read them, let's actually see our first 2-qubit gate. And this is where I introduce the CX C0, or controlled NOT gate. And the C0 gate is the key. It is the key to multi-qubit gates. The reason why I say key is because I can give you any other multi-qubit gate, and essentially it is mathematically possible to decompose it, to translate that bigger multi-qubit gate into just a bunch of C0s and single qubit gates. And the C0 is our unit of or our ability to make one qubit talk or interfere with another qubit. And this leads to very useful properties such as entanglement between two qubits, like a Bell state, or GHZ states, the Greenhorn-Zellinger state, which is like 3 qubits that are entangled. But unfortunately, due to time constraints, I won't be covering those in this workshop. Because I'll be focusing more on the gates themselves and the actual consequences. But the idea behind the C0 gate is one qubit is a control qubit, and another qubit is the target qubit. So if we apply an X gate on the target qubit if the first qubit is in the one configuration, or the ket 1, or the 1 state. So it's slightly tricky, but not impossible, to represent these CXs as matrices, the CX or C0s as matrices. Why do I say it's tricky? It's because of the fact that now that we're dealing with a gate that is sensitive to which qubit is what, we're actually left with different kinds of matrices for the same gate. And I'll sort of give an example as we go on further. So just for now, if our target qubit is the first one, so T is our target, it's the first qubit here, and the control qubit is the second one. Or actually, no, my goodness. There, it's the other way around. The first qubit is the control, the second qubit is the target. You have to kind of excuse me on that little mishap there. Okay, so CX, CT, and you know, why is it that in my coding I decided to put a CT? It's because I have to distinguish between the fact that you could also have it in the other order, which I had it earlier, and I told you guys the wrong way. So I could also have it that the second qubit is the target and the first qubit is the control. So it's the same gate, but it's applied in 2 different ways. That's why I have to be careful in distinguishing between the 2. So if we go ahead and look at this, so the control is this qubit, the target is this qubit. So we're still in 0 and 0 respectively, so nothing changes. So you know, let's read this for ourselves. This is 0, 0, this is 0, 1, this is 1, 0, this is 1, 1. And if I take a look here, that means we have a 100% chance of being in 0, 0, which is exactly what we started in, so nothing really changed there. If we try 0, 1, our control is still 0, so nothing should happen to our target, which is in 1. So if I do the gate again, 0, 1, so this is 0, 0, 0, 1, 1, 0, 1, 1, we're still in 0, 1. So we can clearly tell that nothing has changed. You know, the control is 0, so no X is applied to 1. So the control, 0, and this one is 1. But if we look at these examples here, these two examples, notice that the control qubit is now in the state of 1, and the target qubit can either be in 0 or 1. So if I apply this to 1, 0, I hypothesize that it becomes 1, 1, because the control is 1, so now the X is applied. So let's sort of, do a sanity check and verify this for ourselves. If we look here, this is the chance we're being in 0, 0 is 0. The chance we're being in 0, 1 is 0. The chance we're being in 1, 0 is 0. Okay, that's interesting because I started out in 1, 0, and now I'm saying that we can't be in 1, 0. But notice that we can now be in 1, 1. So the control, the CX or the control NOT gate has actually done something here because the control qubit that I designated is in the 1 state. So if this is in 0, it applies X, so we get to 1. Likewise, if I'm in 1, 1, the control qubit is still in 1, but now my target is in 1, and we know what the X gate does. It performs a 180-degree rotation, a pi radian rotation from along the x-axis. So if I was in 1, I am now in 0, and we can kind of see this going backwards. So what do I mean by backwards? So the bottom here is 1, 1. So if I deduct 1, that means that should be 1, 0. So the sanity check passes, and we're still in good hands. So this is what the matrix looks like for the above examples, where the first qubit is the control, and the second qubit is the target. And it looks sort of like looks like an identity matrix, but the bottom 2 rows have been swapped here. So the CT just means our first qubit was the control, the second qubit was the target. But an example that I didn't show you is CXTC. So in this configuration, the target is the first qubit, and the second qubit is the control. And this matrix, as you can tell, they are not equivalent matrices. The ordering of the rows has drastically changed. There's an interesting thing to be noted about this controlled NOT gate, and it's the fact that controlled single qubit gates are a very common thing to see. And you can actually build them. So you can actually take any single qubit gate and turn it into any arbitrary control gate. And what do I mean by that is you just insert the 2x2 matrix into the larger 4x4 template. So let me give you an example here. If I do np.I4, this is an identity matrix. So just ones along the diagonal, and then that's it. But if I want to make a kind of control gate, I can take the X gate. So this 0, 1, 1, 0 is actually the single qubit X gate. And all I've done is literally kind of inserted it in here, into this lower right-hand corner. And that helps me create a controlled NOT gate. But I could also have built a control Hadamard gate, a CH gate, or maybe a CT gate, or a CS gate, or maybe a CS dagger gate. All I have to do is insert the matrix into that corner. It's a little more complicated for the other way around, where you have to insert the matrix in this middle position here. It's not in the corner anymore, it's in the middle. But essentially, this is what I would call a templatable gate, or in that you can build any number of control gates. So, like a controlled T gate, what does that mean? Well, if my control qubit is in 1, then a T gets applied. If it's not, then it doesn't fully get applied. There's also this swap gate, and swap does exactly what you think it does. It literally swaps the values of the qubits, or to be more specific, it swaps the coefficients. So for example, if we had a configuration of 1, 0, then I get 0, 1. If I was in 0, 1, I get 1, 0. But if I use 1, 1 or 0, 0, it shouldn't really have an effect, or at least an effect that I can't tell. I haven't introduced, or I've opted not to introduce, the idea of global phase. So let's give an example. If I take the swap and I multiply it times ket 1, 0, it becomes 0, 1. And that makes sense. So 0, 0 has a chance of 0. 0, 1 has a chance of 1, and everything else has a chance of 0. So that makes sense. Ket 0, 1 becomes 1, 0. Okay, cool, cool. And ket 1, 1 should just stay 1, 1. So that's that's all well and good. And just to show you guys, let's see for ourselves. Swap does look like this. Excuse me. Yeah, it looks like this essentially. So it looks like an identity matrix, but the middle 2 rows have been swapped. Now, those are some 2-qubit gates, but there are 3-qubit gates as well. And I think I'll wrap up my sort of spiel on these multi-qubit gates around this 3-qubit gate. And this 3-qubit gate actually gets a lot of, there are a lot of names for it: CCX, CC0, or the Toffoli gate after its creator. But it's called, and this is not a typo, the controlled NOT gate. So what does this gate do? It acts like the controlled NOT, but it has an added AND gate. So there are 2 control qubits and 1 target qubit. So the 2 control qubits have to be in the one state to apply an X to the other qubits. So I'll give an example of what this CCX gate does. Notice that our first 2 qubits, I'm designating these first 2 qubits as my control qubits. So if they're both 1s, the X gets applied and it flips the gates here, and as well as the oh, it looks like, hey Amir, thanks for joining. I actually gave you credit for the correcting the matrices over here. So special thanks to you, and thanks a lot for dropping in. I was a little sad you weren't there for me to directly give you the credit, but still glad that you're here. So
thanks, John. Yeah, there's too many. There are too many of these quantum computing meetups nowadays. As soon as this other one ended, I rushed over here. So
no sweat. Yeah. Professor France would have also been here, but he has his own meetup that he's running today. So
that was the one I was at.
Okay, that makes a lot of sense. All right, so I think I was just going over multi-qubit gates. So I'll go back to where I was. I was going over the Toffoli gate, which is a controlled gate, but it has like this added AND condition. And what do I mean by AND? An AND is only true if you feed it 1. So it has to be true and true equals true. It will not be true if you true and false, false and true, false and false. Those all give false conditions. So first, let's generate a 3-qubit state to really see this in action. So if I do, so I'm going to make this ket 111. So it's going to look like this. And the way we do that is we have to do like 2 Kronecker products. So if I do like mp.kron, so ket 1, and then I do another Kronecker product, and then with another ket 1, we finally get to 111. So now let's go ahead and apply the CCX gate. And what do we expect? Before we look at this, it's always a good practice, or it's a good exercise to kind of think about what we would expect the result to be. So if we look at this ket 111, so these control qubits are in the 1 state. So this target should flip. So we should get 110. And let's check here. Okay, so now we have this has 8 entries in it. So let's sort of take a look at this here. We know that the top row corresponds to the coefficient for 0, 0, 0, and the bottom row corresponds to the coefficient for 1, 1, 1. So if I decrement by 1, I get 1, 1, 0. Lo and behold, we have a 1 at the 1, 1, 0 state. So CCX applied to ket 1, 1, 1 will give us ket 1, 1, 0. So this sort of confirms what I was telling you guys about that AND condition. Likewise, if I did 1, 1, 0, it should bring me to 1, 1, 1 because it's an X gate that gets applied to this target qubit. And we can see for ourselves, just looking at this ket or this vertical vector, that does seem to be the case. Now let's look at something where the 2 control qubits are not 1s. So I do 1, 0, 1, and we note that nothing happens. So just to prove to you, this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. So we're still in 1, 0, 1, despite applying the X gate. Oh yeah, here we go. Sorry, down here, 1, 0, 1. So nothing changes. So this is the normal 1, 0, 1, and this is the after applying the CCX or the Toffoli, and nothing seems to have changed, which makes sense because the control qubits are not both 1s. I want to give a note here. The order of the Kronecker product doesn't really matter for ket generation. So what do I mean by that? So notice I could have done, okay, I'll do the, maybe I'll take ket 1, but then I do the Kronecker product first with these 2 guys here. Or I flip the order and I do the Kronecker product first with these 2 kets, so ket 1 and ket 1, and then I do it with 0. The order of your values does. So, notice how these are still 1, 1, 0, and this is still 1, 1, and 0. That still matters, but the way you apply the Kronecker products doesn't really matter too much. I'm going to wrap up all of this gate stuff that I've been teaching you with what happens if we try and apply a single qubit gates on multiple qubits. Let's say that in a 2-qubit system, I only want to apply a Hadamard to 1 qubit. So we don't want it to affect the other qubits. How do we do that? Or what if I want to put n single qubit gates on, maybe n qubits, or maybe n minus 1 qubits, so not all of them. And the Kronecker product comes to the rescue yet again. So let's imagine I want to apply Hadamards individually, and this individually is important, on 2 qubits, so in a 2-qubit system. So I take the Kronecker product of the Hadamard with another Hadamard, so I create this weird HH gate, and it looks, it looks kind of like this. And I do HH times ket 111, or no, ket 11. Ket 11, we're dealing with 2 qubits here, and I do that matrix multiplication, I still get, now I get this thing. And this makes sense. We're actually, all of our qubits are in a perfect 50-50 superposition. Granted, this negative might throw you off, but is not incorrect, because I applied the normalization rule, and I take the absolute value of each of these and I square them, and then I add it all together. It still becomes 1, because if you just do this in your head, 0.5 absolute value is still 0.5. You take the square, so it's just 0.25 plus 0.25 plus, and I just do this 2 more times. That equals 1. So we're still on the Bloch sphere. Woohoo! We're not dealing with thermal or incoherent states, and everything comes out just beautifully. Let's say I want to apply S on 1 qubit and T on the other. Well, I just do this, np.kron, the Kronecker product of the S gate and the T gate. So I get ST, and I get this. Now, you might be thrown off yet again by how large these entries look, but it just has to do with the fact that the imaginary numbers can have some rather inelegant coefficients. At least they don't look elegant when you're looking at them through NumPy's default printing. And you see, if I apply it to 1, 1, we get this sort of combined state. But what if I only want to apply 1 gate? So I have 2 qubits, but I only want to apply a single gate. So 2 qubits, but 1 Hadamard. The trick is you literally insert the identity matrix. So the identity matrix, if I take any quantum state and so I'll just do ket psi, and I multiply it times, so I do the identity times psi, I will still get psi. Nothing changes, nothing happens. So if I take the Kronecker product of the Hadamard gate with the identity, the Hadamard will only target our first qubit, and nothing happens to the second qubit. So if we look at this thing here, we can actually kind of see if this is we can do another sanity check here. So if I take a look at this, 0, 0 has the chance of being 0. 0, 1 has this sort of probability here, non-zero probability. 1, 0 has this chance here, and then 1, 1 has this chance. So what do I mean by the sanity check here? So we can either be in 0, 0, we can be in 0, 1, we can be in 1, 0, and we can be in 1, 1. Now, if I'm targeting this first qubit, that means the first qubit here, the first qubit, has a 50-50 chance of being in 0 or 1. And if you kind of look here, 0, 0, okay, no chance there, but this 1, so we do have some kind of chance bleeding through here, and then bleeding through, and then this 1, and notice that the states with non-zero probabilities have a dangling 1, which is the fact that we applied the identity gate to the second qubit, whereas all of the states that have a 0 on the end, so 0, 0 and 1, 0, have nothing, because they're just not valid states. They're not the ones that we want. So that's kind of the sanity check there. Let's try flipping the order, and this is where order becomes important. So for generating the state vectors, the Kronecker product the ordering doesn't really matter too much. But for generating the multi-qubit matrices, the ordering matters very much. Because if we do like IH instead of HI, the identity gets applied to the first qubit and the Hadamard to the second, and then we get this configuration here. And you'll notice that we don't want any qubits or any probabilities where the first qubit is 0. And that's why like 1, 0 and 1, 1 have these non-zero probabilities. So now we get on to the thing that I want to wrap up this workshop with is the universal gates. So I mentioned in the last workshop that you can approximate other gates with a well-chosen basis set. And this basis set is often dictated by the hardware. So, quantum computing is a huge umbrella term for different approaches. There's ion trapping. I think topological qubits are theorized and in the works. We have yet to see like a fully working model. Microsoft's gambling pretty big on it. There's quantum annealing. That's sort of D-Wave's pet toy there. Continuous variable quantum computing is Xanadu. There are just so many ways to exploit the properties of quantum mechanics to perform useful computation. But each way of doing things, despite being quantum, allows you to have a different set of gates. So some systems might have gates that it can do, but other gates it cannot do. So ultimately, when we develop a quantum circuit, we want to translate all those gates into the ones that our hardware can actually implement. So here are some examples of these universal gates. The Clifford plus T series is very, very common, and it literally consists of a controlled knot and your Hadamard S and T gates. So what I'm telling you with these, I'm telling you that with just these 4 gates, you can give me any quantum circuit, and I can boil it down into those 4 gates. IBM has its own take. They have the U series of gates, so U3, U2, and U1, the identity gates, and the controlled knot gate. And I gave an example in the last workshop over what exactly U3, U2, and U1 are. Now, ion trapping has rich access to these phase gates, but it doesn't really have a direct sort of controlled knot implementation. So there are these things called the icing coupling or icing phase gates, and they're called XX, YY, and ZZ, depending on the spin of the particle you're using. Because remember, ion trapping essentially is you take these ions and you put them in this kind of electromagnetic confinement system, and they're all in like a little bit of a conga line where they're just kind of stuck together, and then you can individually kind of use these specialized fluorescing lasers to change the spin configurations. It's really cool stuff, and if you're really interested, I encourage you to check it out yourself. But I won't go into too much detail. But I'm just telling you that these different hardware implementations have different universal gate sets, and it's just a hardware limitation. So let's actually kind of see this in action. So I'm using this tool here called PitKit. PitKit is created by the Cambridge Quantum Computing Laboratory. And basically, it's this really cool tool where I can create a quantum circuit, and I can tweak it and translate it so that quantum circuit can run on a plethora of existing quantum computing platforms, like what IBM has and what IonQ has, or even Honeywell. Apparently, they have access to the Honeywell systems before we do, as well as Project Q and some other computers that are just not accessible to the public. So I'm going to translate this circuit into the IBM basis. So the IBM basis is U3, U2, U1, I, and CX. So I've created this circuit here. So what I'm saying is, okay, this circuit is we're going to have 3 qubits in our system. All right, fair enough. We have a CCX gate. The control qubits are the first and second. And the target is the last qubit, the 3rd qubit. So notice that this uses 0 indexing, so it's 0, 1, 2 instead of 1, 2, 3. And the controlled NOT gate here, I'm setting the target or the control to be 2. So the control is equal to the 3rd qubit, and the target is equal to the 1st qubit. And then I do a swap between our 1st qubit and the 3rd qubit. So now I'm going to print the circuit out, and it looks like this. This is exactly what I've been kind of saying out loud, and it's what we expect. So this is all well and good. Now I can throw it through PitKit, and PitKit will literally translate my this universal circuit into something the IBM systems can understand. So it's targeted just for the IBM Q computers. And lo and behold, all of these gates are the ones that the IBM computers have, the U1 gates, the U3 gates, and the controlled X gates. So that's what it means. So I can take any quantum circuit and translate it into a different basis. PitKit can, you can define these different compiler passes to get different results. So if I wanted to, I could have done a Clifford plus T pass, and I would have been able to get a different set of gates entirely, but those set of gates would have still represented the exact same circuit that I built up top here. So that's the importance of having these universal gates. And that wraps up essentially a lot of the stuff that I wanted to cover for this sort of last workshop that Quantum Computing at Davis has for the quarter here. So I'm going to go ahead and open the floor to any questions or corrections that you guys have, and I'm more than happy to reiterate over anything I might have went over a little too quickly for your understanding. So go ahead and feel free to ask away.
I guess I can ask a question. Would you be able to share your screen again?
Yeah, absolutely.
Yeah, I was just looking at the bottom part of that, and I was just curious why.
Here we go.
It seems like Pit. How do you say that? Pitkit?
Oh yeah, Pitkit.
Yeah, I wonder why it decomposed that to. Because it doesn't have the CCX gate. Okay.
Yeah, that's what I wanted to show, that the CCX gate and all these quantum gates are, they're still valid gates, but we're always limited by the hardware as to what we can really implement. So you see that with a properly chosen universal gate set, we can decompose any circuit into, for IBM, U3s, U1s. There aren't any U2s in this, but there are a bunch of these controlled knots kind of, sprinkled around.
Yeah, that's cool. So you can basically see the last 4 gates are the same as in the original circuit. Well, the swap gate being 3 C knots, but then all the rest of that is just for that CCX gate.
Yeah. So this is the 3 C knots. Like that's a very that's a good quantum circuit identity to know, that if you put the 3 sort of C knots in this configuration, you've essentially built the equivalent of a swap. Yeah. I know it's different for the ion trapped computers, but even I have a hell of a hard time wrapping my head around what exactly the phase coupling gates do, just because my understanding of the physics behind that is pretty limited. But that's a tangent. I'm going on a bit of a tangent.
I know nothing of that, so that was kind of cool to hear. That's how they do coupling, or that I didn't know that ion trap quantum computers don't have the controlled knot gate that I'm used to. So
yeah, it is a weird limitation, but it's like a small price to pay for the fact that I think you're probably very familiar with the fact that the different quantum computers have different sort of layouts for their qubits, which sort of dictate where you can have your C knots or your swaps, right?
Yeah, the coupling, like on the actual device, which qubits are actually connected to each other, can be coupled with each other. Is that what you mean?
Yeah, exactly. Yeah. So the real cool thing with ion trapping is that all ion trapped computers are guaranteed to have perfect one-to-one connectivity. So if you look at the connectivity, it's almost a complete graph. So every qubit has a connection to every other qubit. And it's just the nature of the laser system they use to control the qubit spins. Like you literally have perfect connections between every qubit.
That's pretty wild. And there are no physical interconnects, right?
Nope, not at all. It's all light and some fancy fluorescing stuff they do. They call it not a Rabi oscillation. There's a Raman, like something like a Raman fluorescence, or there's a name for the quantum phenomena they exploit to get that kind of superposition ability.
Oh, cool. Yeah, someone just, it looks like Kirk confirmed it's Raman.
Oh, Raman. Okay, there we go.
Cool. Well, in that case, thank you all for hosting these. It's been a nice way. It's been a nice way to end the week. That's for sure.
Well, thank you so much for coming to them. I mean, it's a great source of motivation to me, knowing that this content is of use to other people, and I always try and do my best to make sure that it is as free of error as possible and as easy to digest as possible as well. So thank you so much.